computer. All right, this is part 2 for flame retardancy, but this one I stole some slides from somebody else because they had some cool pictures that we hadn't seen before, and I thought I would have a kind of a cool mechanism to go over. So we've talked about these, the gas phase retardants, those are the halogenated materials. The endothermic ones, that's the magnesium hydroxide or aluminum hydroxide, and then the char forming, and that's what we've been focusing on most there. And so when we're looking at that char forming, you have to disperse your clay pellets a lot, and then you'll see this good cone calorimetry curve where you have low heat release, low peak heat release, and you have, and then what's also best is if there is a delayed time to start burning. If there's a delayed time to start burning, that's also best. But they came up with their idea here to show you that what this looks like when it's actually happening. So polystyrene actually depolymerizes if it's not actually combusting, it can depolymerize just with heat. In this case here, they're showing after 50 seconds, 90 seconds of this, it's just decomposing and volatilizing off as a gas. When it has a filler in it, this is only 5% montmorillonite here. We can see that we start forming a char layer, and then that char layer kind of alters and fuses together. And then in our final, after 240 seconds here, this is what remains. It actually puffs up and leaves an insulating layer. Notice above the level, or almost above the level of the pan, where it's below the level of the pan here and here, but it's almost above the level of the pan here. So that's actually puffing up and giving it that a resistance to heat flow and giving it that. And so they came up with, this is the one slide I really want to whole presentation, is the critical criteria for the formation of a homogeneous char is a homogeneous dispersion. We've seen that before in mixtures that were not very mixed very well. We didn't see a marked improvement or a good improvement here. Things that seem to be mixed pretty well, or things like, whoa, why is that doing so well? It must be because of a very good homogeneous, because you want as the stuff burns out in between your filler, you want it to get compacting layers. If it's only spotty around here, it'll be able to ablate in other ways. And so you actually see on these two here, they're fairly smooth surfaces after the combustion test. And the round ones are just a flame top. These are actually the same samples that you would use in the cone calorimetry test. You use these 10 centimeter by 10 centimeter by 1 centimeter samples. And you'll see that there's a lot of disproportionation in the char, a lot of cracking, and a lot of places where the material was burned through and had that. So this slide I thought was really cleverly done and showed a lot about that. Okay, so the rest of it is not something I want to work on, but I wanted to show that one slide because I thought it was really good. Okay, so let's continue on with our systems. We were all the way up to magnesium hydroxide fillers. And in this one here, they're going to use a polypropylene that's made in India, and they make their nano hydroxide in situ. So what they're going to do is they're going to take a magnesium chloride, usually, and do a hydrothermal synthesis to create the magnesium hydroxide. Now, it's a hydrated magnesium hydroxide, but it's also not a spherical particle. It turns out these form plates like montmorillonite. They don't have this mechanical strength that montmorillonite has, but they do have a palladium type surface. Okay. So by looking at that, we can say because of its platiness, we're going to look at the different fill factors here. And if you have, you see this rise in tensile strength until you get overfilled, and then you start getting aggregation. So we're looking here, maybe 4 to 5% is where you want to be. Again, impact strength goes down. Why? It's becoming more brittle because there's more of a brittle material in your matrix, right? And actually, magnesium hydroxide platelets are really, it's almost like talc. They're very brittle. And so not only do you get a decrease in impact strength, but now you're actually getting that basically you're filling that cross-sectional area of resistance with things that aren't helping at all. So even though they're plates that you'd expect to do, montmorillonite actually improves impact strength to a certain degree, but these are soft plates, and so they do not increase the the impact strength. But as all plates do with some kind of constrained polymer theory, is you do increase your Young's modulus, you do increase your hardness with this increase in material. Notice again, this is because the polymer next to that is not allowed to freely move as well as in the bulk. So those little areas of quote, a almost chemical cross-link that's making it tougher as far as your modulus and hardness go. But then let's look at our rate of burning. Okay, so this is the rate of burning, and this is seconds per millimeter. So the longer is better. Okay, so we start out at 2.4 seconds per millimeter burning through, and they get all the way up to 3.8. So it's almost twice as slow, just with our 14% loading. 15%. So that is substantial. Okay. Now they didn't do the cone calorimetry sets, but that would have been their next thing to do. I guess they don't have a cone calorimeter, or they don't have that much material to work with. Okay. So moving from that to ethylene propylene dye ene. So it's basically ethylene propylene butadiene copolymer. They're very rubbery, and in this case they had 4 different materials. They had 3 different macroscopic or micro, and then 1 nano. Okay, and so these were sieved at different levels, and so this is 1 micron or 10 microns right here. So all of these particles are fairly large, and they're aggregates because we should see platiness in our magnesium systems. Okay, and so basically a whole look at theirs. So if we compare the macro to micro in the limited oxygen index, we don't see much of a difference within the set. At 8 parts per million, we start to see a little bit of change. At 10 parts, maybe a little bit of change. There's not really much difference in the limiting oxygen index between the micro and the nano. Okay, and if we look at this right here, this is the again, these first 3 are the micro, and then this is the nano here. All the micros were about the same, running around 350, but look at the nano. The nano is 100 kilowatts per meter squared lower. 100 kilowatt. That's a significant difference. Okay, and if you look at their heat release, the curve isn't exactly ideal. The curve we're looking at is this one right here. It comes over here. It has a secondary heat loss, which is probably after it gives off all of its water, it's going to continue to combust. Okay, so but overall the area under the curve was lower than these because I guess the heat was not faster. And then if you look at the tensile strength versus nano versus the macroscopic fillers, we see moderate improvements, linear improvement for the micro, which we expected. And then of course we see what we see for the nano as well. We see a max benefit until you start aggregating, and then it goes down. So that was a pretty good one. The net result for especially the peak heat release, right here, the 100 kilowatts lower was a significant pop. Okay. All right. So, but what this paper actually did a lot of other stuff. They did a lot of other mechanical analysis on there, and they went on to go to talk about what they call the pain effect. The pain, named for a person, not because it hurts, and is that the elastic storage modulus, at some point, the frequency of your fillers will help up into a certain frequency, and then they'll all coalesce down to the upper limit. So what we see here in both of these, in both the micro and the nano here, but notice the nano is higher. it has a higher storage modulus here with the frequency. And then at a place right around here, this 100% strain, it goes down and it goes down, it tapers down. So it has an effect until it reaches a point where it's just being pulled out. So that was we hadn't talked about pain effect on there, and it's really a rubber thing. So we'll see that again. But then let's look at that heat release again with these nano right here. Again, the nano is the triangles right here. So the triangles, they actually go up and come here. And this is a much better curve than we saw for the other magnesium hydroxide, where it had the second burn peak. This one has a little one, but it's not the major one. So your peak heat release is still here, 250, and then tapers down quite substantially. So it is working as a nanomaterial. And notice that only the smallest of the macro sizes matched its curve, right? So let's see. So they're all above it. Yeah, all the heat releases are above it on the macro. On the micro materials, only the nano has a significant decrease in that heat of peak heat of release. All right, so now we had another group that actually made their own, but they didn't make it just as a platy little suspension. What they ended up making is these little flower-like spirits. Okay, so they used a similar hydrothermal process. So they took the magnesium chloride and water and some base, I think. And here they used an additive that was the glycine. So that's an amino acid. And so that glycine changes the dynamics of how the plates form. So what they have here is they have a regular SEM image on the top, and then a field emission SEM image of them, and then a TEM. And from the TEM, they were able to get some of these separated out and get an X-ray pattern of what the plates look like. So we have this hexagonal plate array. Okay, so it looks like that they have platelets. These are the actual these are individual platelets of the magnesium hydroxide, and they're about 60 nanometers thick. But why are they flowers? Why are they flowers? Well, they did put through a mechanism of how they think it works. So in the hydrothermal process, what you have is you're degrading your aluminum, your magnesium chloride into magnesium hydroxide, and then those start to do chelation. They start binding together with the additive, in this case, the amino acid. And then they start nucleating. Once they start nucleating, then they can actually start forming the plates. So they nucleate first, and then they start growing preferentially in an axial way. So you get these plates, and it's a hexagonal array along that plate line. But now that these plates are forming, they don't aggregate by flat, flat, flat. These are actually aggregating into these flower-like structures. And so that's why they're getting this different. Oh, and this is the amino acid that the magnesium starts to chelate to until the oxygens start taking over and start building. This is where the oxygens are displacing the amino acid as it grows into the plates here. So having that amino acid on the outside of there changed the dynamics of the growth. And they didn't form just plates, they formed the spherulites. Okay. Now this is a naturally occurring phenomenon. There are minerals that look like this, but are also hydroxide-based minerals. So of course, did it work? Well, turns out at 1%, it didn't work at all, had the same heat response curve. But at 5 weight percent, which is not bad, usually you use it in 50 to 70% weight. You did actually see a nice change, delay in onset of ignition. You have a flat peak and it comes down, and flattens out really well. And so if we look at this one here, our total heat release is less than either of the other ones by about 10 megajoules, which is significant. That should be that would be in thousands most of the time. And the peak heat release is almost 200 degrees lower, over 200 degrees lower. So It's doing its job there, and the onset time is twice as long as with the unfilled material. And then they also showed it with this DSA. This is the differential scan. This is the actual weight loss here. So we see amazing weight loss, and then it kind of tapers off. And this is just the ADS, and this is with the 10% right here. So we see the heat given off. I mean, the loss here is quite strong, but then we have a higher charging yield as well. Notice this is on baseline, 0 charging yield. This is above baseline, somewhere around 1 or 2%. So probably as magnesium oxide. So they were able to show those things. And so, I mean, it's interesting that nano, if it's well dispersed, can still have some effect, even though it's such a small fraction of what it is compared to the macroscopic composite systems. Okay. So in this one, they kind of changed it with 2 different rubbers and used the same thing. There's styrene butadiene rubber, and then there's the propylene butadiene rubber. And they made their stuff by hydrothermal formation, but instead of using that amino acid, which gave them the plating spherulites, it gave a solution of polyethylene glycol. So it has a bunch of oxygens on it, and it made more of the platy nanoparticles. Okay, and then when they made their composites, they graphed them and said, oh, look at this. Our flame retardancy in millimeters per second is substantially better than with conventional magnesium hydroxide. The author of our book kindly quoted, however, the difference between the conventional magnesium hydroxide and the nano magnesium hydroxide in both polymer systems was insignificant, although Patel et al. Claimed that the nano material provided a significant increase in flame retardancy in the SBR resin to the conventional filler. Now, let's analyze this statement. That was kind of mean to have to put, right? But if you look at here, the difference in time between this one and that one is half a second. Half a second per minute. So you would have to take that on high-speed film and measure that. So I agree with the statement, although I would have said it nicer. But this is a case where it got published because, well, I said it was good, and the reviewers looked over it and said, okay, and it got published. But anyway, yeah, that was, I thought, something that the book had that was kind of funny. So, and we're going to be doing literature review here next, so we'll start to talk about that. Okay, so let's move to epoxy. And in this system here, they're going to use a mixture or either the macro or the micro here. So this is the nano stuff right here. This is the micro stuff right here. And you'll see that only, it's these edge platelets, and they're kind of broken up to make them know they're barely, I want to say they're close to, 200 nanometers, not 100 nanometers, but oops, there we go. So they were really good about theirs because it's an epoxy resin. They used a 3-roll mill to do their system, and they had a neat design of experiment. So in this design of experiment, they did nano, micro, nano, micro, nano, nano, untreated, meaning they didn't use surface treatment on it, micro, and micro untreated. Okay. And they found that they all have about the same density, which is what you'd expect with that kind of filler level. Notice the density is increasing as the filler level increases. So here are their results, okay? And it had some interesting stuff here. Okay, so just the EP polymer itself has a TG, which doesn't really change much. The time to ignition is 58 seconds, okay? So notice that none of the time to ignitions change much. There's no delay in that ignition time, okay? But the peak heat release rate is significantly different in the nano materials, especially the 10% untreated and treated right here. Significant difference in that heat release, okay? From it's 400 kilowatts lower than the virgin And it's still about, let's see, it's still, maybe 50 kilowatts lower than the macro size material. So there's still something happening here. The total heat release doesn't really change that much, and the total smoke is all lower every time if you have any of the additive at all. So total smoke produced is per, and if you look at their curves here, while the numbers look good, there's not a significant change in the shape of the curve. Okay, they're all burning like plastics. Okay, so while there is a decrease in this max heat as you load it up in 10%, it's still, so the total heat is less because they're all tapering out about the same. The max heat is the one that changes. Now, again, to be really, really good for max heat, so it doesn't set other things on fire, you want it preferably below 200. So, well, there is an improvement here. It's not, we're going to make this into a material. Okay, so our next system involves POS. And I don't know if I talked about the mechanism of POS working. So POS is, a cage of silicon atoms. And so when they thermally decompose, it folds out and turns into silicates. And so you end up with the silicates forming. So you can imagine you have it like a molecular clay that opens up when it gets thermally decomposed. And so that's its mechanism of how it works. And so they had some interesting stuff here. With polypropylene by itself, it has like a heat rate of 1400, and that's in kilowatts here. You get a 40% reduction just by adding some POS to it. Okay. Now, in this polymer system here, which is a polyamide and I don't remember what that polymer is. By adding a little bit of the POS to it, you get a 65% reduction in that peak heat. And with the styrene butadiene styrene rubber here, you get a 42%. And in a lower loading, notice this is a lower loading, right here, 90 SB rubber, 10% POS, 80 rubber, 20% POS. You get 42% and 27% reduction. So just by having that 20% in there, which looks like a good number here, you can get substantial change. And then, of course, the mean heat loss is lower in all of the POS systems. But look at this. Smoke doubles. It becomes a sooty, smoky, white cloud. So you're giving off silicon oxide as one of your volatile materials. So smoke more than doubles when you have this higher loading in the SB rubber. Oh, I'm sorry. The SB rubber is smokier than these. But notice that in the POS system here, it didn't go down. In the POS system, it didn't go down. It did go down in these, but in this one, from here to here, smoke went up, and smoke went up. Here they didn't, because it was so smoky as it was.
Could that be like a good thing? It's like excluding oxygen?
Excluding oxygen, as well as taking away heat because of the volatilization, can be good. However, in a lot of industrial and home applications, the idea is you want to have as little smoke as possible so first responders can do the job. And in the case of aerospace or spacecraft, you want zero smoke. So,
like silica smoke is extremely bad, right?
Yeah, because it's so easy to absorb at that point because it's so small.
Yeah.
And if it goes in your lungs, I'm not sure it's a fast case of silicosis, but it's definitely not an advisable thing. Okay, so the last section in our book goes through what he calls multi-component FR systems. And so they can combine nanomaterials. They can do just nanomaterial combination or nanomaterial and a fire retardant material also. Okay, so this way you get the best of both worlds. You get the engineer saying, you have fire retardant in there, right? I said, yeah. but then I have my nanomaterial too. So you get the best of both worlds. So in this case here, we're looking at EVA, and that's that ethylene vinylene acetate copolymer. And then we looked at different ways to do it. And in this case here, we started with just purified multi-wall carbon nanotubes. And then we just crude multi-wall carbon nanotubes because it's hard to purify. And if you can use the crude one, why not? Right? Because we're not looking for electrical properties or optical properties. We're looking for them to soak up heat. So maybe the crude will work just as well. And then we have the organo clay one right here. But then we have this one. We have purified and we have organoclay added together, just a little bit of each, just to see what happens. Okay, if we look at our peak heat release rate, our EDA, that's about 600. A little bit of carbon nanowalls, it's starting to drop. Okay, a little bit of clay, it starts to drop. A little bit of the crude nanowalls, it drops a little bit, but look what happens right here. A little bit of one, a little bit of the other. It's the lowest number there. It's, good 210 degrees lower. And that's not even the highest loading, that's like the lowest loading. So what their use for this was they wanted to use it for cable sheathing, okay? So they wanted cable sheathing that would withstand a test we haven't seen. And that's another reason I'm showcasing this particular paper in the book, is that they have a test that is a UL requirement. And what you do is you hold a cable, 12-foot long cable, you ignite it at the bottom, and you see how far it burns. Okay, so in this case here, the maximum temperature you can get at that end of 12 feet is this 850 degrees F. If you go above that, you fail. Okay, so the neat compound by itself, and this is with aluminum hydroxide additive, which is normal one of those. It got reached 1930 degrees and completely burned the entire thing. It burned above the cable, so it's a fail. Okay, complete fail. Now, by adding the same amount of this and the nanofiller, which is the mixture of carbon wall nanotubes and the clay, the max temperature it got to at the height of that, at the top of that cable, was 620 degrees F, and it's self-extinguished at 6 feet. So all they had to do was add that nanofiller to a compound. There's a significant difference. Now, I love this test because it's like, what does that little dip in the cone calorimetry mean? Well, it can mean a lot on a different test. So I thought this test was really valuable. It's showing that that 210 degree difference in the peak heat loss is significant in other tests out down the road. Okay.
The crude nanotubes would have the same effect as the purified ones, but it makes them pretty similar.
I have that data here. We didn't use that. The same author went on to do it in polyethylene. And so they're going to do low density polyethylene and compare and contrast the crude versus pure. So thank you for the question. So in this one, they also did some other things. They also did a raw bender, a laboratory mill, and then a co-kneader and a co-extruder. Okay, so they used different processes, and they actually looked at how the process changed the cone calorimetry results, which is kind of cool. So in this case here, we're looking at how much of your polyethylene you have. Then you have the single-walled carbon nanotubes at 2 loadings, at crude and purified, right here. And so let's go off to the results. Okay. So let's start with the multi-walled carbon nanotubes first. The polymer itself is the top curve there, and all of the loadings, both crude and purified, all had a decreased peak heat output right here. Some of them are pretty low. Some of them are even below 300. This one right here, the 5% purified walls. And so we have a significant drop. That's 200 degree drop right here. Okay, so hey, the multi-wall carbon nanotubes seem to be working. Okay. All right. So let's look at the single wall carbon nanotubes. Gosh, they all have higher peak release rates. So that's like, okay, so their conclusions were single wall carbon nanotubes do not act as flame retardants in low density polyethylene. I agree. The multi-wall carbon nanotubes act as flame retardants in polyethylene with no reductions on time to ignition, contrast to organic clays, and with reductions in heat release. So let's look at that statement here, right here. So we do see delay onset. Now, maybe 10 to 15 seconds max here, but we do see much more delay onset. We saw like 60-second delay in onset with the clays. So we have that there. And then the crude multi-walled carbon nanotubes have the same heat release reductions as the purified. So to them, the crude and the purified multi-walled carbon nanotubes work the same, which makes sense because we're looking at for its bulk property, not the little stuff hanging off the outside of it. It doesn't matter. And of course, there might be some, broken ones or little ones or whatever. But then they went on to do two different things using the same formulation. They blended their same formulation by two different methods. One was the lab rolling mill, one was the co-kneader here. And so from this curve, which do you think dispersed the materials better?
With the rolling. Wait. What's the reduction?
That's the reduction in, no, that's the release rate, release heat rate. So I think the co-kneader has the lowest heat release rate. Okay, it does have the bimodal here, but the heat release rate on the roll mill is higher. So I think it's
What's the heat release rate improved with the multi-wall carbon nanotube? I thought it was just the delay.
no, the heat release rate was improved with the multi-wall. It was, all of them were less than the pure polymer. And they all seem to have a little dip and then an up, except for this one, the 5 to 8% seem to have a nice flat curve. So it seems that the processing of this is going to be neat. And if you think about it, a bar bender is just, kind of like this cup mixing like this for a while. And the co-kneader is probably something similar, but has a different blade design. So you get a little more shear. Okay, questions on that? So I thought that was a neat study because they used different processes and they've used clean and dirty, and they used two different kinds of materials all in the same system, all analyzed the same way, and they came up with some pretty decent conclusions on that. Okay, so now we're going to shift gears a little bit. We're going to look at a resin used for a laser sintering. Okay, so the laser sintering, you need to dump in enough heat to get it to fuse, but you don't want it to ignite. Okay, so the idea here is that when you have these resins, you want to have them be able to be centered with your laser and not catch the whole powder bath on top. Okay. So this paper actually was really cool because they actually gave the processing parameters that they used in their extrusion method, which is not usually there. So I wanted to go through these. The first one right here is just a montmorillonite clay with our polyamide 11 right here. The feed rate for the polymer and into the thing is 3 kg per hour. Screw feed is 250, and then see how it rises to the middle and then it goes down. Okay, that's the temperature in degrees C. So at the feed throat, it's going to be 464 degrees, and that's to get it to start melting and pulling it in. Then it's going through the maceration blades, and then that's about where you're adding your clays in the second zone. You add your clay, add some powder to it, and then it goes through your high shear zone. and your temperature is always higher in your high shear zone, you have a lower viscosity. But then you lower the temperature again because when you try to extrude it, you don't want it to just out the end, you want it to come out as a filament. So they cool it down until it gets to, and then the pressure builds up here, and then you can get your filament. Okay, now when they did the carbon nanotubes, they used a carbon nanofiber, sorry, they used a slower feed rate and a slower screw speed, but the same temperature profile. Okay? And notice their torques are about the same here. And then when they did all three of them, plus a flame retardant material. So they have the montmorillonite, the carbon nanofiber, and the flame retardant material, which I want to say is a phosphate on this one. I'll go on the next slide. Little bit slower feed rate, a little bit faster here, same temperature profile. Because the temperature profile is controlled by the polymer. The temperature profile is controlled by the polymer. But notice the torque spec's higher. Okay. When you add in two different kinds of material, a platy thing and a long thing, plus a filler, it gets a little bit more resistance flowing through the system. Okay, so let's look at their results here. So I want to say their flame retardant material was aluminum hydroxide, I think. But if you just look at none of it together, you get a V2. Nylon gets a V2. So it drips, but it doesn't do too bad. The lowest loading on montmorillonite in there fails. Okay. But if you add the flame retardant, it passes. Okay. And if you add a lot more flame retardant, it passes. Again, without the flame retardant here at the higher loadings, it fails, but with the flame retardant, it passes. So, I mean, do you need any of those things in there? And this is what one of their fails would look like right here. Formulation 1 here, that's failed because it burned all the way. This has flame rise all the way. The flame stops on this low end. See, this is where the flame is rising to. This is the flame front here. It's probably here. The flame actually went up the side here. Okay, so the conclusion they came to was that, yes, the clay helped because of the heat release. Okay, so let's see, that's nylon. Yeah. So they said that there was, actually they did not do cone calorimetry on these. They only did that. They assumed that the clay or the nanofibers were helping hold the structure together so it wouldn't rip, and therefore it gave them better response. All right, so now let's move on to EVA, which is ethylene vinyl vinyl alcohol. So that's the EV, acetate, sorry, ethylene vinyl acetate. And so when they did just organoclay, multi-wall carbon nanotubes, and then both together, they saw a significant difference. Clay by itself is this curve here. Multi-wall carbon nanotubes are this way here, and notice it has a delayed onset. And the C, which is here, and I believe is also on this one right here, is just a little bit lower for heat release, but it has a lower char gain as well. So in this case here, there was a little bit of a synergistic effect because it doesn't look like there was an effect of the clay in there at all at 5 parts per 100. But by adding the multi-walled carbon nanotubes, it helps. Now, what might be is that the multi-walled carbon nanotubes are the only thing that's happening. But notice that we're doing 2 different aspect ratio materials. 2 different aspect ratio materials here. So maybe they weren't just very well dispersed. Okay, so now to prove that they are right, they did it again and they changed the loadings to, they looked at the EV with that and the EV by itself. And the nanotube and the one with clay, again, overlay each other almost the same right here, except that we have a later onset for both of the ones with the carbon nanotubes. So there might not be any synergistic effect of having that clay in there, but the nanotubes were definitely helping the process. So one thing that the clay did help with was the structure of the material after burn. Okay. So what they see here is in the heat release rate here, that with the, oh, it's knocked off, sorry. Okay, so let's look at this side first. And so the just adding them on perlite does delay the heat release, the ignition time. Oh, I'm sorry. The organomodified clay it speeds up the ignition time. It catches fire earlier. How's that possible? The EV by itself is 84, and now it's 67. And then we add the carbon nanotubes back, and it goes back up to where it was. But then when we add both of them together, they're not as good. But look at the heat release rate. The organoclay by itself helped a little bit, but then having both of them in it together helps even more. And then look at the cracks right there. The EV itself has lots of cracks because there's nothing forming the char layer but the organic material itself. The clay helps with cracks because it forms that nice silicate layer on top. And by having them both together, the carbon nanotubes don't create as good a char layer because they're cylinders, and so it doesn't help as much. But if we look at, let's see, there we go. EVA clay. So we see decreased cracking compared to this. That's what they say. This is, yeah, the multi-tubes. This is the hybrid between this one and that one. And they say those are better. If you look at the top ones, I think that really says it. The clay EVA has a lot of cracking on the surface. This one has a lot of cracking on the edges, but this has a fairly clean feel. Can't tell the difference. These might be on the bottom. The ones at the top definitely agree with their assessment of cracking.
Yeah, but I would give it a 0 if it still has cracks like that. Is that not the right one?
That is the right one. Maybe there's a threshold of 10% or something.
Maybe or if it goes across all the way or something.
Yeah. So, yeah, I do not know how they analyze that, unfortunately. Seems like there would be a better, and this is after using it on the, this is what they're analyzing after it's gone through the cone calorimetry. So they did some other heat studies here, and they're looking at this, the binary mixture, and they're kind of drawing some conclusions that it's the heat release is changing or the weight loss of mass is changing here. I don't see a significant difference in any of these, and so but the heat release rate was a significant change. That was definitely tangible. And again, I don't think you can avoid a heat release rate or a cone calorimetry experiment by trying to use TGA. I don't think it is an appropriate supplement. One instead. So then the book goes into mechanisms of fire retardation. And one of the cool pictures that were here is the idea that as the matrix burns away from the clay, remember you have that matrix keeping them apart, and if that matrix wasn't there, they stack back together. And so that's what they're doing. They're actually stacking back together to create that char layer. And that char layer is that thermal resistance barrier and oxygen resistance barrier. So this is probably the clearest diagram of that in the book we have. Now, they also came to this set here. Well, they were looking at different composites here. This is an epoxy. One is the neat resin, which fails completely and is burned. One has about 10% of the POS material in it. So as it's burning, it's laying out a silicon dioxide layer on the surface here. And they get, when they swing it out, it does extinguish here, but it's still not classified. Because for a V0, it has to self-extinguish in 10 seconds. For a V1, it has to self-extinguish in 30 seconds. They both missed by 30. They both missed 30 seconds. So they had most of the material here, and they had no drops. So that's great. But then the cotton ignited for this one right here. So they have improved it, but they still don't have their V0 or even a V2. So I noticed that when we were talking about all these things, we've done films, we've done like big layers and something like that, but I haven't talked about fabrics. So I got a paper on, and there isn't anything about it in the book either. So I got a review article on it to talk about nanocomposites on fabrics for flame retardants, because that's actually one of the things I'm doing myself as part of my research. So I thought maybe you'd like to, well, not the nanocomposite part, but the other. So there's a bunch of different ways that you can do this. There's nanoparticle absorption. So just get an active nanoparticle, soak your fabric into it and do it that way. Then there's layer by layer of assembly, which is a little bit different because you're using alternating positive and negative things to get the things to stick. Then there's a sol gel and dual cure process, which is where you're growing the particles inside the fabric. And then you're kind of squishing out the water at the end to get it, or solvent at the end. Then there's a plasma, but then they have talked about the biomolecule deposition, which I'm not going to cover. Anyway, so in the particle adsorption, that's pretty simple. You just kind of wash your system in there. But in the layer by layer assembly, it's a little different. In the layer by layer assembly, you have to have alternating cation followed by a rinse, followed by an anion. So you're going to do electrostatic adhesion, rinse off all the extra electrostatic adhesion and keep building that up. Okay, so this would work with montmorillonite clay. Actually, the sodium chloride actually is one of those things that will disperse in water. So this is just kind of your rinse, wash, rinse, and repeat system here. And to do this on fabrics, they actually use both natural and non-natural, and then they used a variety of different things. So in the case of in the case of cotton, this is cotton here. They use lanthonite, which is a natural clay. It doesn't have much charge as montmorillonite, but sodium montmorillonite is one of the really good ones too. And then they use polyethylenamine, which has a positive charge nitrogen on it. And what they saw was they got some the afterglow for the montmorillonite treated one was 10 seconds faster, meaning it extinguished faster than untreated cotton. The residue in the cotton fabric was adherent and non-fragile when you use montmorillonite. So it's almost like you were making a lantern mantle. Have you ever seen a kerosene lantern? Kerosene lanterns, when you first get them, you have this nice flexible little baggie that you hook on there, and then it centers out when you do it. And it turns out there's it's a thorium zinc oxide, no, zirconium oxide that forms the mesh after you center it out. It's really fragile after, but it's flexible. And so there's that, you know, that having a coherent and non-fragile system. With just silica and aluminum coated silica, so there's no organic binder at all. You're looking at completely inorganic binders. You actually get a 20% reduction in peak heat release. That's significant for cloth. And then if you use POS system, so this is a POS, one's cationic, one's anionic, and reduce weave structure and shape it into a fiber to highly preserved. So it's creating that silicon layer on the surface of the fibers as it were. So you got to try this stuff on polyester because that's more common. So we're going to do polyester fibers. And with silica, aluminum coated silica, so it's the same guys who did it on the cotton here. they see a 45% a decrease in cone calorimetry. Oh, sorry, 45% increase in time to ignition. So it takes longer to ignite, 20% reduction in the heat elimination, and reduces burning time by 95% and eliminates melt. For polyester fabric, that's amazing. Okay, because it melts and drips and it's really bad. So that is a really good result. And again, there's no organic binder. It's completely inorganic. So and then we have zinc phosphate nanoplatelets with 3 different types of ion. That's the cations here. We see that increase in time to ignite for just the polymer-based one, decreased peak reduction by 26% by the one with POS, and the nanoparticles get a smoke reduction by 25%. So, and the CO2 is increasing as well. So the aluminum nanoparticle with the zinc zirconium phosphate system, the inorganic system with no organic binder, actually performed really, really well and did not produce as much smoke. Okay. So again, these were all done by dip, up to 100 times or so.
So what did they? So it eliminated the dripping completely.
That's what it says. Eliminates melt, dripping, and all. So, and so if you can imagine, as it's sintering, you know, there's going to be at least enough of the inorganic material is fused not to hold things together to keep it from letting melt. Okay. So then they tried some hybrid organic and inorganic, or adding an intumescent material, a material that will expand or give off, or does the release of heat. So in this case here, the intumescent is the ammonium polyphosphate right here, or the sodium phosphate here, or this one right here. And this amino acid derivative is the intumescent material, and the polyacrylamide is as well. It kind of swells the chart. So in the aluminum phosphate lens and the Kaizen, right here, they see a suppressed glow, they see a lower peak reduction, and they can see that, and that's in a polyester, cotton-rich polyester. So it's mostly cotton, a little bit of polyester, but they saw reductions using that kind of mixed materials. The aluminum-coated silicon nanoparticles, again, are making delayed ignition and decreased heat release. The phosphate system was deposited just on cotton fabrics and decreased it. Again, they did it by microcombustion calorimetry. It's not the full cone calorimetry, which is a better experiment because there's a lot of micrograms can set you off. So it's not as good an assessment, but block of flame propagation with that one, delayed onset with that one, graphene oxide, delayed onset and delayed peak when put on cotton fabric. So graphene oxide is great for fabric because again, it's water soluble and you can get it to electrostatically adhere to your cotton fabrics because they have a high charge to surface ratio. Okay, so then that's one way to do it, but it's really much faster if you can spray. Okay, in this particular way, this is they can spray the polyanion and the polycation, and they don't lay down as a compact layer, but they do lay down as layers, and they do counterbalance each other. So what we see is that number one, it's a faster production rate. You can produce it faster because you're doing by spray. You don't have to dip and hold. And so the results they got from that, from these Langmuir Blodgett by spray, and they use the inorganic only system here. They got the same results they got from dipping that they got delayed onset, they got delayed peak and total smoke. Okay, so just so they went from the dip, or that took like hours, to a spray system which took minutes, and they got the same results. So the LBL can be tricked with the co-spray system. I actually had a project where we had a rotating drum that would and it had 4 sprays on it. And it was a rinse, a cation, an anion, and a rinse. And we made films like this thick over like several hours. It's kind of cool. Okay, so now let's switch over to the sol gel process. The sol gel process, it typically is the hydrolysis of a metal compound that creates a metal oxide framework. Okay, so, and when it's done, typically you would put your materials in something and then it would kind of set up and make these nice little particles, and then you have to process them. However, you can, and one of these people did, were able to do it into a system where you dipped it into your bath that has all of your components in it. So it infused it into the fibers. It went through some nip rollers, which squeegeed off the excess, and then went through an oven, and in the oven it finished out the sol gel process. So what does that make it? It makes it a viable process. And the fact that they could demonstrate it on fabric. And fabric is a great roll-to-roll thing because that's how it's made and that's how it's processed. So that is a great way to go. So in the case here, most of the time when people were talking about sol gels, it was to make super hydrophobic fabrics, so self-cleaning fabrics. Okay, but what they found out was that if you use the right stuff like silicates and stuff like that, you can actually turn them into flame-resistant materials as well. Okay. They're still super hydrophobic, but they are also in reduced flammability state. Okay, so in this one right here, I wanted to show this bit with it. I don't have any results on this one, but this is actually the sol gel process that they're using these organically modified materials, and they actually made electrically conductive sol gel cotton. So now this would probably also be pretty good char resistant because the high nature of the fact that it's the carbon black system, but they didn't test it for that. But I thought it was kind of cool. Anyway, so in this case here, we're looking at time to ignition and heat release rates. This is cotton by itself. This is cotton by itself. Notice time to ignition does not change very much with this system, the sol gel system. But we do have a decreased heat, an increased heat release rate with the alumina. We do have a decrease with the silicon. So it does delay onset and decrease heat, but not significantly. It is true, this did delay onset and this did have a lower peak, but we're looking at 80 to 100 or 80 to 90, so that's less than 9%. So right there. Okay. So here is a different set of data from another thing, where they're looking at cotton by itself, and this is total smoke release right here. By adding silica to it, you actually decrease the smoke quite a bit. Ammonium pentaborate and the boron phosphate did not decrease smoke significantly, and that is a maybe. But this silica with the zinc oxide is definitely releasing less smoke, and it actually changed the peak CO2 release as well. And it increased the CO. So that was kind of cool that we were able to see at least something was helping with decreasing smoke from fabrics. Okay, so the last thing that they were talking about here is coatings from plasma treatments. And they were specifically talking about cold plasma. And so in cold plasma, you're available to surface modify your material by reacting with different ions. So if you're going to react it with CO2, you're going to put carboxylates on the surface. If you react it with oxygen, you get hydroxyls on the surface, not amines or nitrogens, or you can even do halogenated materials as well. So then, you've prepped the material for the inorganic material, and then you can actually plasma in things that generate inorganic materials directly, either from organometallic volatiles or organometallic involatiles that you've already infused in your system. And then that can start to react with the surface as you plasma. But then they can also do a two-step process where they plasma first, and then they treat the material. And usually that gives you a better adhesion because then you have controlled plasma on your surface. But you can also use low pressure plasma, which is actually atmospheric plasma. You can actually do it in atmosphere. atmosphere now using radio frequency. And so you can get surface activation, plus you can feed a low volatility monomer into the nozzle as you go. And so as it hits the plasma, it gets into its reactive state and then reacts with whatever plasma it is. You can actually do that. And again, you can use just organics, graft, like plastics or organometallics that'll decompose. Okay. And then with that, you can then use the plasma to etch away the surface so that all your organics are gone from the surface and you have your only inorganic surface layer. So that's going to help protect you from oxygen. Well, that works really well for your organosilicon compounds, especially if you use an oxygen as one of your gases. It will oxidize the entire surface down to SiO2 and way up on the surface. And then you can also use nitrogen plasma technique for that, but that's usually to bond other polymers too. So you take acrylic monomers, nitrogen plasma is a little bit softer, and you can graft stuff onto that. There were no pictures on that. I'm seeing some cool plasma stuff. This article didn't actually have pictures. Okay, questions on that? So that was fabrics. Okay, so now the last thing, I think the last thing I want to talk about is flame retardants at interfaces. So one way to study this on a mechanistic scale is to do single layer or small layers and figure out how they react. Okay, so in this case here, we're going to use what we call a Langmuir-Blodgett technique. In the Langmuir-Blodgett technique, you guys know what that is? Okay, in a Langmuir-Blodgett technique, what you do is you take a bath of a fluid, preferably a fluid your material does not interact with, a fluid with high surface tension, usually water. Okay, you then have gates on it, and then you have a sample just dipped into it. Then what you do is you continuously push the things in, and you're looking with microscopes to make sure that you have the entire surface of your thing is covered in exactly one layer of molecules. Okay, so you have one layer of molecules. Imagine you've seen a drop of oil on like multicolored oil patterns on a puddle. Okay, if you took your hands and started doing this, the colors would change because it's getting thicker and thicker, thinner and thinner. You know how you do it. So then as you're moving these together, you're getting one layer perfectly aligned on the surface. And then you start pulling up your sample, still pulling in this. So your two in walls are coming in. Your sample, now this one's etched silicon wafer. And what happens is the materials, as the water de-wets from it, the solid material stays adhered to your plate. Okay, and most of the time you just do a one layer film on that, but if they're healed well enough, you can dip down, up, and you can multiple layers. So you can actually get multiple. And these are perfectly structured because you're actually measuring the surface tension change. You get these that are called isotherms, which is a graph to tell you exactly how fast to move your walls. Anyway, so once you get that, you can get different things later on here. So what we're looking at is we're going to layer clays on there, one plate at a time. One plate at a time. So they get perfect layer. And so that when you take it out, you're going to have this nanoparticle layer on your surface, and then you're going to take this, yes.
Is it difficult to get the clay one layer on the corner?
Yes. Usually you might have to use something else, but the Flowsite in particular has quaternary ammonium salts in it. I think you can use oils, you can use other things. I think they use water. Yeah, they use water. And if you don't, if the clay is not fully wetted, it will sit on top. So it has to, basically hydrogen bonding on the top and bottom. If it doesn't have that, it will float up. There's probably a trick to it. But anyway, so what they were able to do was they were able to see that they could make the nanoparticle layer And then they dropped the liquid on here, and they saw that the different types of clay have different surface tensions here. This is an organomodified clay. This is an organomodified clay. This is the sodium salt of the clay as it comes out of the ground. Actually, it probably comes out as a mixed and purified. So what did they see from this? Well, when they did this, they then incorporated it into a composite. Okay. So we have the sodium one there. It doesn't look very well dispersed. We have this one here, and then we have this one here, which looks very well dispersed. And of course, the small angle X-ray scattering shows us this. We have D spacing of 1.5 nanometers, so that makes them stacked. We have D spacing here, 3.69 nanometers, so that's partially intercalated. And then this right here, because there's no peak here, if you're not seeing this hump here, there is what they call fully exfoliated. So it's able to get to fully exfoliated. So imagine you're starting with single platelet or platelet groups here, and then you're layering them down layer by layer to get them thick. Okay. So then they looked at their flame resistance, and again, we're looking at the same three in order here. But in these, this is before they did flaming, and this is when they did flaming with an additive. And see how it's really carbonized down here. But notice the microstructure here. This microstructure here is where the clay platelets that were burned out around are starting to form that char layer. So we have a structured foamy char layer created by the montanillinite plates at two different loadings here. And this is going to be heat resistant and have less heat flux because of the high layer. Here, this is bare polymer. It's a heat. Okay. So what are the results from here? What they saw was that the polymer by itself has a high heat release rate, but all of the composites that they had lower rates. Oh, wait, hold on, that is an additive. That is something phosphate. That's a flame retardant additive. That's just a flame retardant additive. This is close right here. We see a peak heat release rate here. It's lower in all of them. And the higher loading of the clay worked out really well. And then the total heat release is lowest with the 2% clay as well. Melamine polyphosphate. So melamine polyphosphate is a common bulk additive used as flame retardant material. It's usually used at 15%. Yes.
So do you think that they could get exfoliating their clay because they were still in the same?
I think it was the best exfoliated. The montanillinite was the best exfoliated of the set, but I agree with you. There are tactoids right here. Yeah. So, but there are a lot of little things there. But compared with that, this is the additive.
Or it's the shadow of the, I think it's the shadow of the curves, maybe?
No. See, this right here is the additive, the melamine polyphosphate, and that's in all of them. And so the dark spots might just be the melamine polyphosphate. So, but the melamine polyphosphate might have wetted the plates, and so it's elongated. I think those darker, bigger areas are the melamine polyphosphate. So I think it is fairly well dispersed. All right. And then they looked at it in a different polymer system. This is with EVA, yeah. And this one's a little different in the fact that they use weird additives. Okay. They used actually up to 3 different additives. They used aluminum hydroxide as the endothermic possibility. They used molybdenum sulfide because it's a plating material. So it's a plating nanomaterial. You can actually exfoliate it just like graphene. And it has the same lubricious effects here. And then they used graphite nanoparticles. Okay. And so nanoplatelets, sorry. nanoplatelets. And so by they're showing that these right here, you can see the spots here are going to be different loadings of the plates. The numbers are different loadings of things. And so we're looking for where is the molybdenum, where is the aluminum, and the carbon dioxide. So they see that it's fairly well dispersed. It's fairly well dispersed in this system as well. Okay, but that's a weird mixture. Aluminum hydroxide, okay, I get the endothermic thing. Aluminum sulfide, okay, it's platy. But then why have the carbon nanoplatelets, graphite nanoplatelets? It's also platy. But maybe they won't stack. Anyway, so let's look at their additives here. So the first one at the top is the polymer by itself. And it has a huge peak right here. It's completely burned out by 30 seconds. So the next one is just with the aluminum hydroxide. Okay, no other thing, just the endothermic effect here. And that's this red line here. And we have a nice peak here, but it burns out fairly quickly as well. So the aluminum hydroxide is doing a good job. It has lowered it by almost half right here. Then if we look at just the aluminum plus the graphene the black graphene platelets, you see we get a nice change. The onset's still at the same place the other two were, but it's a nice low heat release rate, probably the peak being below 500, significant reduction in peak rate, but no change in onset. Now, by adding the aluminum and the molybdenum, that's where we see a change in the onset. We see some help. It's not as good as the last one. It wasn't as good as with the graphene nanoplatelets. But then this last one is with all of them. It's with the aluminum, the graphene nanoplatelets, and the molybdenum. And it's the lowest of all. Has the lowest heat release rate, and it has the onset. It's lowest as well. I mean, highest onset temperature. So they thought, okay, that's pretty cool. Graphene should help more than it did, but let's kind of come up with a plan. Let's come up with a theory about how it works.
Still, none of them has the perfect charring, right?
Right. Well, I mean, the ideal char. Nobody has that yet. Okay. So here's their plan of what's happening. Okay. So we have our matrix. We have our aluminum unburnt. As these big particles here, we have our plates and our graphite plates. So these platelets are our aluminum sulfide. The dark ones are the graphene platelets. Okay. So we start out, it's all nice and dispersed. And what happens is as the heat comes off, the aluminum starts losing water to give off heat. That's what it's supposed to do. So that layer comes off there. And then as the matrix burns away, we get a concentration of the graphene nanoplatelets and the molybdenum nanoplatelets. Well, graphene can burn if there's oxygen, okay? Especially if it's graphene oxide with a lot of defects. So what can happen is as it's continuing to burn, all the carbon and all the matrix goes away. You're left with the dehydrated aluminum hydroxide and the molybdenum sulfide, generating a compact and structurally sound layer. The nanoparticles of the dehydrated aluminum hydroxide would not create a structural layer, but the platiness of the molybdenum sulfide plates kind of binds them together to give us this nice char. Okay, and that's why we have a second peak in our heat release rate. You see this, it's burning out almost all, it's delayed start, burns out most of your matrix here. Now the carbon nanotubes start to burn, and then we're left with nothing else. So that's their explanation for not being a perfect curve. Okay. And then the last one is what we call, they wanted to look at the binary system. So it's mixing two different polymers together and then two different flame retardants together. In this case here, they're going to start with antimony trioxide, which is used as a burn rate inhibitor. And then we have the decabromo biphenyl ether, which is of course used as a vapor phase inhibitor. So it creates radicals and does the big thing. So this actually does an interface surface, and this does a big interface. So they get it mixed, but then, you know, it was okay. But then they started adding Chlorosite 20, so clay product, to see if they could get it better. Now, they didn't mix too well. We see some exfoliated plates, but we also see phase separation between the polystyrene and the PMMA. Okay. And actually, you see phase separation in here as well, polystyrene and PMMA. So what happened when they did that? So let's look at it. The cool thing about this is they did an interesting process comparison. They injection molded their pieces to do one sample, and then they 3D printed their samples to see if there was a difference in the 3D printed one versus the injection molded. Okay, so imagine you're wanting to certify your 3D printing filament as a fire resistant material. You got to taste it, you got to test it after doing the filament process. So they did that here. And so what they did was they looked at their molded versus this, and this is a UL 94B, and then this is limiting oxygen index. It's molded and printed, both extinguished in the first second, printed, extinguished 4 seconds, but molded is 2 seconds. What do you think caused that change, that slight change?
It's better dispersed and printed is kind of
Like spacing between layers.
printed at the layers.
The layer,
interborn.
there's a little bit of air gap in some of the layers somewhere. There's a little gap there, making the heat transfer lower, making it distinguish a little bit slower. So I think there's the little defects that you get from printing, but it's not significant, and it still gets you a V0. So that's really good, and neither one dripped. And the limiting oxygen index didn't change. Of course, that's an exterior bulk thing. But I think that slight change has maybe some little gaps here and there. And then when you look at the other properties here, impact's a little lower, modulus a little lower, tensil's a little lower, elongation's a little lower. Because of those little defects, you know, they're not fully intermingled together, they're just sort of slightly intermingled. So, I mean, but it's really good. I mean, it's pretty good. I mean, it'll serve a lot. And if you look at the heat release rates, we have good curves. They're really good curves. They're about the same, molded and printed. They start about the same and they end about the same. So overall, I would consider this a pass for a 3D filament being as good as the bulk, or as close to the bulk. So the conclusions from this chapter are to the idea that, you know, there's several trends going on. One trend is that by adding 2 or more nanomaterials together, there's a synergistic effect. We saw that with clay and nanotubes a lot. Okay, the clay is helping inhibit oxygen, nanotubes are helping transfer heat, and you get this nice synergistic effect with the lowest heat release rates and some of the lower smoke production. Okay, montmorillonite is always considered one of the best materials because it's so cheap. They dig it out of the ground. Okay. Now, some of the other ones, like the double layer hydroxides, or low oxide tubes, or some of the other systems, those have promise too, but they're so much more expensive because you have to make them. So they have to really, really do a lot better job than clay, or else they're not going to be worth the time and money. Okay. And another trend, which we saw in the last half of this talk, was adding a fire-resistant additive, but you don't have to add as much as you had to add before. You can add 10% instead of 30% and get the same when you add a nanomaterial with it. So getting a synergistic effect with your additives and nano-sized materials, you can get the benefit you want where you have a much lower loading. And if you have a lower loading of your fire-resistant material, you might have better physical properties. Okay, and that's my last slide. And it's 3:20. So yeah, and of course I put this on Canvas if you want to go with that. But again, most of the stuff came from the book except for that the last couple of things.
So
All right, I'm going to stop recording.
why do you think the nano or better